Thank you. So we want to build a utility scale quantum machine, something that delivers a commercial value. And the question I want to address is, what do we need to build for that? What is the architecture? Because fundamentally, quantum computers are novel. While new technology has accelerated your computing, advanced it, the latest the GPU works on the same principles as the abacus. Nothing has changed in 4,500 years in the way we compute. Has gotten faster, but there was no fundamental change. That has changed with quantum computing. With quantum computing, we'll compute in a fundamentally in a different way. And so the question then becomes is, how do we have to build the quantum computer? What do we build differently than a classical one? What is needed to reach the scale? And for that, I always like to start with the applications. What are the problems that we will solve with the quantum computer? It will not be a general purpose machine, but it will be an accelerator for specific problems. And which ones those are, that's not clear yet, but we have the first guidance already. We know a quantum computer will be more complex than a classical one. The logical qubit is more complex than a transistor. The operations thus are slower per operations, but the quantum computer has quantum speed up, and thus it needs fewer operations for certain problems than a classical one. Now, with the logical qubit being about 1 billion times more complex than a transistor, we need lots of speed up. We need more than the quadratic speed up. We want to look for problems with the exponential speed up ideally. And because the clock speeds are slower than classical clock speeds, I/O will be slower. And so we want to look at problems that have low I/O and big compute and big speed up. And there are some problems we know where quantum computers they will have a big impact. One is cryptanalysis, breaking codes. That will be a topic of the next panel. The next is, though, that the real impact will be in chemistry and material science, solving the quantum systems. Those applications we know already. And thus my question now becomes, what do we need to build a machine that can solve those chemistry problems, that helps us design new chemicals, new materials, new drugs much better than we can do classically? We'll do that in a hybrid way. We'll use AI, HPC, and quantum. We already now in the last years, and it was emphasized by last year's Nobel Prize, saw how the AI is changing the way we do science. We train models based on the results of HPC simulations. The models we trained with that are then used for much faster the simulations. We've used it to design a battery and a coolant and more. So we accelerate science with AI. But these models we train today are only as good as the training data. And the simulations of classical computers for molecules, they are approximate. We see the molecules in a blurred way only. But when we have a quantum computer, we can do the accurate, exact simulations of the molecules. We see it much sharper. then we can use those results for training better models. And so the future I see for quantum, one of the first applications will be that we take the quantum computer to refine the classically pre-trained models, to get models that are fast for inference, but are quantum accurate. So that's the vision I have for the first applications. That we basically use the quantum computers to teach quantum physics to an AI. And then the question now becomes is, how do we build such a machine? And there, quantum computers, I think, are computational accelerators, like GPUs, FPGAs, and we can learn lots about the architecture of the quantum computer by looking at the architecture of a classical the supercomputer, of a classical GPU machine, for example. And as we build it, learning from decades of classical computer architecture, we'll see what we have to build for quantum, what is similar, I think most, and what is different, just a bit. When I look at the stack, at the top, we are writing the program in a high-level language, classical and quantum. We compile it down to an intermediate representation, then to the executable, and then classical and quantum will have the ISA layer, the instruction set, the architecture that is the contract between the programmer and the hardware that abstracts away the details of the hardware so that we can write code that works on all systems. And just like in the classical CPU, then within the CPU, the instructions are converted to the microcode that runs on the micro architecture of that version of the CPU, and the programmer doesn't have to know that. On the quantum side, the equivalent are the logical qubit operations, the exact type of qubit, the exact type of the QC code that can be hidden from the programmer. So it's basically the same stack, classically and quantumly. And then we can do resources estimation, that is, we compile the program down to the ISA, we run it on a simulator, we get a profile just like in the classical world, and then we use the profile with the model for the time needed for the logical qubit operations to estimate the runtime and the number of the qubits needed. Just like, again, in a classical case when I design a new CPU. So the architecture for the quantum system in the cloud is the same as the classical HPC architecture. On top, the workloads, developer tools, the cloud services, the cloud, and then the hardware. When I zoom in here, the workloads they will be AI-centric. They'll have a co-pilot to run them with natural language. They'll combine AI, HPC, and the simulations, and they'll run on hardware. That hardware can be general compute, HPC machines, GPU machines, large memory machines, or quantum machines. There's no difference. In the data center, the quantum computer will simply be yet another SKU that I put in, and it fits into the same data center architecture. When I then look more closely into the quantum machine, the accelerator, there again, the architecture can be modeled very closely after a classical accelerator. So on top, we'll have the developer tools to write the code, and these can be the standard ones. Well, once it's Visual Studio Code with the GitHub, your Copilot, and vibe coding works classically and it works quantumly. So you can't just type in VS Code, write the code for Grover's algorithm in Q# or in Qiskit, and it works, and then I can just type in and run it on quantum hardware, and those things magically work since this April. So it's great to see how if we use the classical tools, how all the classical progress applies to quantum computers. Then when we look inside, on the top of the machine, we'll have the quantum operating system, like on a classical machine. For the settings, setup, the configuration, the use management, the job management, and to run the quantum codes. Some parts of the code will run on a classical CPU, the classical hardware, just like in your laptop. Classical code, and some parts will run on the quantum piece. And for the quantum piece, the specific quantum computer may differ. And for each one, the quantum OS will, like in the classical world again, have a quantum driver that compiles the code to the specific backend we have now, and then runs it on that system. And then we have what we call the quantum engine. That is what takes the quantum instructions and runs them on the hardware. In the classical world, that is like the architecture of the CPU. It takes the instructions, converts it to microcode that runs on the hardware. Quantumly, it takes the logical qubit instructions, converts it to the operation for the specific QC code chosen there, and then converts it from the logical operations to the physical qubit operations and sends the control signals then down to the qubits. On the way up, the measurements are passed through the QC decoder to correct the errors and make the logical qubits. So when you map it that way, then you see how the quantum architecture maps well to how we build the classical system. The engine that is for the GPU, nothing but the graphics engine of the GPU in the same way as the GPU executes the instructions on the graphics units here in the quantum engine that takes the logical qubit instructions and runs them on the quantum hardware, which is the bottom layer. So to finish, we see that the architecture of utility scale the quantum machine will be quite similar to a classical one. I hear many questions. How should we deal with distributed computing in quantum? How should we deal with different modules? How should we deal with the code optimization? And in many of these cases, my answer is, let's look how it was done classically. Let's look at what worked classically. And in all cases, so far we found that the classic solution applies also to quantum. That's great news because it means once we have scalable qubits, then we already know how to build the system. And that will accelerate the path to building utility, the scale machines. And in the coming weeks, the month, I will publish a series of articles and videos explaining the stack, explaining kind of how what we learned from the classical world can be applied quantum and can help us build the utility scale machine. Thank you.